we found this was going to be negative d dr of tau r equal to 0. We looked at table 2.4 and found that tau can be written as negative mu dvz dr. And so we can make that replacement. So tau is going to be replaced in our differential, so we can get a velocity profile, right? We know that this is telling us that the shear times the radius is constant in our system, right? This is equal to 0, the derivative, so this is constant. And we want a velocity profile out of this, so we will replace tau, negative mu dvz dr, equal to 0. And now we can assume that constant mu, right? We don't have this function. We're just going to pull out we can pull out negative mu actually, let that negative cancel. And we know that mu is not equal to 0. Oop, and we forgot r. Right, that's what makes this a unique solution compared to what we had before. But r is still here. So we can cancel mu and end up with dr of r dvz dr equal to 0. So that is now our second order differential that we're going to be solving. This one isn't too bad. We can just solve this with antiderivatives. If you want to get very technical, your math professor would probably tell you that you need to reduce the order of this with a substitution. I'm going to tell you we can just take two antiderivatives. This function, the derivative of this function with respect to r is 0, so this function is equal to a constant. I'm going to divide over r, so it's c1 over r, dvz dr is c1 over r. And if I take one more antiderivative, this is going to be, if I kind of separate this, I can say this is c1 natural log of r plus c2. All right, and so there is our velocity profile. We'll need to choose a couple of good boundary conditions, and we'll be able to figure out what these integration constants are that we introduced here. So our boundary conditions are going to be from the no-slip condition at the inner cylinder, Ri, and the outer cylinder, Ro. But we were going to do a little bit of work to write that this inner cylinder, right, is being pulled with a force. And this force we can write as the force is the shear times the area of this cylinder. So the shear on the wall times the surface area. This had an outer radius of Ri, the inner radius. So this should equal the shear at the wall times 2 pi r L Ri. And that way we know this isn't some sort of variable, right? The force is equal to a constant. All right. That looks pretty good. And at the outer cylinder, we had Vz must equal 0 at the outer cylinder. At R equals Ro. And let's see, we can make use of this first boundary condition. Let's do that first. Fx equals, we again have the shear at the wall is negative mu dvz dr times 2 pi r I L. And the first derivative, we can kind of cheat. Again, we've already solved for this during the derivation. So we know dV/dr is C1 over R. dV/dr. Evaluated at the wall. So evaluated at Ri, because we know this is C1 over R. So this boundary condition can become Fx equals, let's move this stuff out front here, 2 mu pi Ri L dV/dr is C1